Okay, so one of the strategies that I talked about to handle that really crazy question in the warm-up is to break up the question into smaller ones. We've been talking a lot about how um, one strategy that comes up over and over and over again when differentiating is to look from the outside in. And hopefully you've heard me talking about the concept of the Russian dolls. So we know that if we take this idea, we take the Russian doll part is you deal with the big part first. You open up the first big piece, and inside it is another one just like it. So in order to tackle this, you have to take the first big one, you take the outside, and then you go off and you look on the inside. And that might mean that you're done, and there aren't any more dolls left, or you got to open that doll and you get a new one, and you go down smaller and smaller and smaller. So that concept is really important for the chain rule, and it's how we're going to tackle that big long one. Instead of looking at as one big differentiation, let's look at smaller ones from the outside going in. So the chain rule addresses that and just formalizes what we already know. So we'll just take a second to write it down. And right now it may not make total sense um, until we actually see it being used. So if you have two functions, then we'll write down that if y is a function of u, and u in turn is a function of x, then if we want to differentiate y with respect to x, we go through some steps. We go from the outside in. And it's hard to envision what I'm talking about in this setup line if y is a function of u, which in turn is a function of something else. But we'll see an example in a moment. So just copy this down. If y is a function of u and u is a function of x, then what we do is we do this. We say the derivative of y with respect to x is first from the outside, you do the derivative of y with respect to the derivative of u times the derivative of u with respect to x. And essentially what it's saying is the original function dy by dx is so complicated that what we did was we set this intermediate step called u, and we define this middle step. And we have to differentiate that middle step before we go off and do the whole thing. Now, if you look at the statement I just wrote in green, it makes total sense. I want to differentiate y with respect to x, but I need this intermediate step. So I first differentiate y with respect to u, and then go inside and differentiate u with respect to x. Now the reason this works is because I could cancel this du and this du and end up with dy over dx, which is what I want. Now we use this concept when we do the power of a function rule. So for example, if we had 2x minus 5 all to the power of 7, what we actually are doing are pretend this is the inside one is its own little function. We first differentiate that, so it's 7 times its own little fraction to the power of 6. That is like your dy by du step. But then we know that we have to go the step further and differentiate inside like its own little function. In this case, it's just 2. So we've actually been using the chain rule before when we use the power of the product or power rule, power of a function rule. It's just we haven't formalized it. And it's important to understand that it doesn't just work for just this one example. It can go further for 3 functions, 4 functions, 5 functions. And sometimes you'll take something crazy and break them into small intermediate steps and realize you have to take the derivative of each of those steps. Just like the Russian doll, we take the big picture, take that doll apart. Inside is a new doll. You do something to it. Inside it's a new doll. You do something to it. And eventually you differentiate all the small little pieces. So for 3 functions, if y is a function of u and u is a function of v, and v is in turn a function of x, then we'll have all the steps. And we'll have dy by dx is equal to dy over dv times, or sorry, du, and then du over dv, and finally dv by dx. So for three functions, it's the same as for two functions, but we had to go through a second step. So dy by du, and then du by dv, and then dv by dx. Just means you go from the outside, differentiate the outside, to the inside, and then inside even further. So if we take this concept and apply it to something we already know, let's revisit the one we did in the warm-up B. 2 minus x cubed to the power of 50. So we know, we have a rule for this, the power of a function rule. But let's see how it would look if we formalized it using the chain rule. What we would do is say this. We would say let u be its own little function inside here. So we're going to make the question a little bit easier and change it then to, instead of 2 minus x cubed, we're going to call it u to the power of 50. And now when we differentiate dy by dx, we say, hey, okay, y is no longer a function of x, it's a function of u. So I have to use the chain rule. First differentiate its own function, dy by du, but then we know we have to actually go inside and differentiate du by dx. So the math is very similar. It's 50, except it's u this time to the power of 49. And then we look inside times, and now we differentiate this like its own question, which is negative 3x squared. Now we can go on and replace u, put it back in to what we know it is. We know that u is actually 2 minus x cubed. And then, of course, our final step, as always, is simplify when it's appropriate. In this case, we multiply the first and last terms. I get negative 150 x squared, 2 minus x cubed, 49. Now, you might look at this and say this is overkill for the warm-up B, and it is, because we already have a rule for something to the power, a function being raised to a power of 50. But the chain rule will allow us when we have more complicated ones, when we have a bunch of different functions within one big function. So let's start assigning things so we can just make the math a little bit easier. We differentiate in the outside and then eventually in the inside. So that's where we'll move on to example 2.